The light goes straight from the star to your eye, right? Straight line, simple. But the universe doesn't work that way. And the reason it doesn't is gravity. Let me think about this problem the way Einstein did, but I'm going to approach it differently. See, Newton had an idea about gravity. He said objects attract each other. There's a force between them. And this force depends on their masses and how far apart they are. That's the law of gravitation. Every object attracts every other object. Now, Newton even thought that light might be affected by this force. He wrote about it, but he wasn't sure how to work it out mathematically. Here's where it gets interesting. 200 years after Newton, we had a better way to think about gravity. Not as a force pulling things together, but as something that curves space itself. This is Einstein's idea. And when I say curved space, I don't mean space is like, well, space is hard to visualize, but let me try. Imagine you have a rubber sheet stretched out flat, nice and smooth. Now you put a bowling ball in the middle of that sheet. What happens? The sheet sags. It curves down around the bowling ball. The heavier the ball, the deeper the curve. Now, if you roll a marble across that sheet far away from the bowling ball, the marble goes straight. But if you roll it closer to the bowling ball, it curves. It follows the dip in the sheet. It doesn't roll straight anymore. That's what mass does to space. It curves it. It warps it. And here's the incredible part. Light, which travels through space, has to follow that curve. Light doesn't go in straight lines around a massive object. It gets bent. Now, why would anyone think light should be bent by gravity in the first place? Well, light carries energy, right? And energy is related to mass. That's Einstein's famous equation, E equals mc squared. So you might think, well, maybe light has some kind of effective mass, and gravity can pull on it. Maybe light curves the same way a baseball curves when you throw it. But here's what's beautiful about this problem. It's not actually about light having mass. Light has no mass. Light is massless. The reason light curves isn't because gravity is pulling on it like gravity pulls on you when you jump in the air. No. The reason light curves is because the space itself is curved. Light is just following the geometry of space. It's taking the straightest path available to it. But that straightest path is curved because space is curved. This is so strange when you first hear it. The light is going straight through curved space. That's the trick. Okay? So if this is true, we should be able to see this happening. We should be able to measure it. But there's a problem. The sun is right there in the middle of our solar system, and it's very bright, and the stars are far away. The light from those stars reaches us after traveling billions and billions of miles through space. But when that light passes close to the sun on its way to us, the sun's gravity curves the space, and the light bends a little bit. Now, how much does it bend? Newton calculated that if you assume gravity is a force pulling on light, and if light had mass, it would bend by a tiny amount, about 0.87 arc seconds. An arc second is 1/3600th of a degree. So we're talking about incredibly small deflections. But Einstein, when he worked out his theory of general relativity more carefully, found that the bending should be twice as much, 1.75 arc seconds, exactly double. The difference is huge for a physicist because it means something fundamentally different is happening. It's not Newtonian gravity pulling on a massive particle. It's curved space-time. The geometry of reality itself is warped. But how do you test this? You can't see stars when the sun is nearby because the sun is too bright. The light from the sun drowns out the starlight. You would need something to block the sun's light while still allowing you to see the stars around it. You would need a total solar eclipse. And this is where history enters our story. It's May 29th, 1919. A total solar eclipse is happening. Arthur Eddington, a brilliant British astronomer, leads an expedition. His team goes to 2 different locations to observe this eclipse, one to Sobral in Brazil, another to São Tomé in Africa. They're bringing cameras, telescopes, and plates for photography. They're looking for stars. During the eclipse, when the moon blocks the sun's light completely, Eddington photographs the stars that are around where the sun is. These are stars whose light passes very close to the sun on its way to Earth. He carefully notes their positions. Then, months later, when the same stars are visible at night far away from the sun, he photographs them again and notes their positions when the sun isn't nearby to bend the light. When he compares the 2 sets of photographs, he measures the difference. The stars have shifted. They're in different positions. The ones near the sun have been displaced. And when he calculates how much they've been displaced, the number comes out to 1.75 arc seconds, Einstein's number, not Newton's. Can you imagine the excitement? The Royal Society of London holds a meeting. Eddington stands up and says, "After a careful study of the plates, I am prepared to say that there can be no doubt that they confirm Einstein's prediction." The implications are staggering. Space itself is curved by mass. Light follows that curve. Einstein is right. Now, I want you to really think about what this means. What it means is that when you look at a distant star through a region where there's massive gravity nearby, you're not looking at where the star actually is. You're looking at where the light curved around the gravity. The light that reaches your eye has taken a curved path. It left the star going in one direction, but gravity bent it, and now it's coming toward you from a slightly different direction than where the star actually is. In some cases, and this is the really fascinating part, if the geometry is just right, if the star, the massive object, and you, the observer, are lined up just perfectly, you don't see one star. You see a ring of light, a complete ring. It's like you're looking through a lens made of gravity. We call these gravitational lenses. Or sometimes you see multiple images of the same object. One piece of light from a distant galaxy gets bent around a massive galaxy in front of it, and it arrives at us from multiple different directions. So we see the distant galaxy not once, but 2, 3, or even 4 times, all from the same light source, bent different ways by the gravity in between. This was all predicted by Einstein in 1936. He said if you have perfect alignment, you should see either a ring or an arc. He thought it would probably never be observed because the chances of such perfect alignment seemed impossibly small. And he was right. For a long time, nobody saw these. But eventually, as telescopes got better and astronomers started looking more carefully at the sky, we found them. And they're everywhere. They're one of the most powerful tools we have for studying the universe now. But let me come back to the basic question. Why does this happen? What's really going on? Light travels through space, right? And the speed of light is always the same, about 300,000 kilometers per second, always. You can measure it in a laboratory, and you get that number. You can measure it using light from distant galaxies, and you get the same number. The speed of light is a constant. Now, when I say light travels in a straight line, what I really mean is that light takes the shortest path between 2 points. In ordinary flat space, the shortest path between 2 points is a straight line. But in curved space, the shortest path is curved. It's not a straight line anymore. And light, doing what it always does, takes the shortest path. It goes straight through curved space, which means it ends up on a curved trajectory. Think of it this way. Imagine you're on the surface of a sphere, like Earth. What's the shortest path between 2 cities? It's not a straight line on the map. It's an arc. It's a great circle route. An airplane flying the shortest path between those 2 cities would follow that arc. To someone in flat space looking at a map, it looks curved. But to the airplane, it's going in a straight line. It's just a straight line on a curved surface. Light does the same thing. Space near a massive object is curved, like the surface of a sphere or a valley or a saddle. Light takes the straightest path through that curved space. To us, watching from a distance, it looks like light is curving. Now, here's something beautiful about this. If you think of space as curved, a lot of things suddenly make sense. Why does gravity pull things toward the ground? Because you're on a curved surface. You're falling into the curve. An object released from your hand doesn't fall straight down toward Earth's center. It follows the curvature of space around Earth. That curvature just happens to point toward the center. And this explains why a feather and a hammer fall at the same rate on the moon, because they're both just following the curvature of space around the moon. They're both taking the straightest possible path through curved space. It has nothing to do with air resistance or different masses falling at different speeds. It's pure geometry. Okay, so here's another thing I want you to think about. The title of this talk is The Light That Never Left the Star. What do I mean by that? Well, in some sense, every photon of light that leaves a star is shaped by the gravity in its path. None of it travels in a perfectly straight line. Some light bends a little bit, some bends a lot. Some light bends so much that it never reaches us at all. It curves back, or it curves around and around in loops if there's extremely strong gravity nearby. Around a black hole, for instance, there's a region where space is curved so extremely that light curves back on itself. Light can even orbit a black hole going around and around. It's trapped in the curvature. In a sense, that light never leaves the star, or rather it leaves, but it comes back, or it stays in orbit. Even for normal stars, the light that reaches us has been slightly bent. We're seeing a star through a gravitational lens. We think we're seeing where the star is, but we're really seeing where the light curved to reach us. So in a very real sense, the light that reaches us from distant stars has been bent by gravity, redirected, diverted from its original course. But there's something even more mysterious I want to talk about. Imagine a star so massive, so dense, that nothing, not even light, can escape its gravity. As light tries to leave that star, the gravity bends it more and more and more until it curves back down. The light never actually escapes. It's pulled back into the star by gravity so extreme that it overcomes light's attempt to flee. This is a black hole, and this is the ultimate example of the light that never left the star. The light didn't just curve a little bit. It curved so much that it never got away at all. Now, I want to think about why this matters. Why should we care about light being bent by gravity? Well, first, it's one of the most important confirmations of Einstein's theory of general relativity. Eddington's measurement in 1919 wasn't just an interesting observation. It was the moment when scientists collectively said, okay, Einstein is right. Space is curved. Gravity isn't a force in the Newtonian sense. It's geometry. Second, this has become an incredibly powerful tool for studying the universe. When light from a distant galaxy gets bent around a closer galaxy, we can use that bending to measure how much mass is in the closer galaxy. We can study the invisible matter in the universe, dark matter, by looking at how much it bends light. We can map the distribution of matter in the universe by studying how light gets bent and displaced by gravity. Third, it's philosophically important. It tells us something deep about the nature of reality. Space isn't just an empty stage where events happen. Space is real. It has properties. It can be curved and warped. And the curvature of space is what we experience as gravity. Let me try to explain this even more carefully because it's tricky. In Newton's picture, gravity is a force. You have mass here, you have mass there, and there's a force between them. It's instantaneous, or at least Newton left that question hanging. But the force pulls, and everything is affected by this force equally if they have the same mass. In Einstein's picture, there's no force. There are no invisible lines of force pulling things together. What happens instead is this. Mass curves space and time around it. Everything, matter, light, particles, whatever, has to move through this curved space. And because it's curved, things that aren't near any other object will move toward the object. Not because they're being pulled, but because that's the direction the curvature goes. You might say, but that's just pulling with extra steps. And you'd be forgiven for thinking that, but it's not. Because once you think of gravity as curved space, a lot of other things become clear. You can ask, what's the relationship between space and time? Can time be curved too? Einstein said yes. Space and time are woven together into something called spacetime, and spacetime can be curved. Massive objects don't just curve space in 3 dimensions. They curve the 4 dimensions of spacetime. They curve how time flows too. Time runs slower near a massive object. Time runs faster far away from it. This sounds like something from science fiction, but it's been measured. We've put atomic clocks on airplanes and flown them around the world, and they've run at slightly different rates depending on their position relative to Earth's gravity. This is why general relativity is so different from Newtonian gravity. It's not just a correction to Newton's law. It's a completely different conceptual framework. It rewrites our understanding of space, time, and gravity itself. Now let me tell you something interesting. Not everyone believed this right away. Even after Eddington's measurement, there was skepticism. Some people said, maybe that doesn't prove what Einstein says. Maybe there's some other explanation. And in a sense, they were right. You can construct Newtonian theories where light gets bent too. You just have to assume light has mass and is affected by gravity in a Newtonian way. You'd predict half the bending that Einstein predicts, but still you'd get some bending. The fact that Eddington measured the Einstein value and not the Newton value is what proves Einstein is right. It's the ratio that matters. It's the specific amount of bending that tells us we're not dealing with Newtonian gravity on a massive particle. We're dealing with curvature of space-time. But here's what I find fascinating. Light being massless might seem like it shouldn't interact with gravity at all in the Newtonian picture. A massless particle wouldn't be pulled by a Newtonian gravitational force, but light is pulled. Light curves. Why? Because light moves through space, and space itself is curved. That's the beautiful insight. Let me think about this from a different angle. What if we lived in a universe where gravity was still a Newtonian force, but somehow it could still affect light? Well, it could only affect light if light had mass. But if light had mass, light would be slow. It would have an inertial mass that resisted acceleration. If you tried to accelerate light, it would resist. But light always travels at the same speed, always. Nothing can speed it up or slow it down. So light can't have inertial mass. But Einstein showed that inertial mass and gravitational mass are the same thing, the equivalence principle. If you have an object, the mass that resists acceleration when you push it is the same as the mass that feels gravitational force. So if light has no inertial mass, which it doesn't, then it can't have gravitational mass either. And yet light is bent by gravity. How? The answer is gravity isn't pulling light. The space containing light is curved. Light isn't being accelerated by a gravitational force. Light is following a geodesic, a straight line through curved space. This is the crucial distinction, and it's what makes Einstein's theory so different and so right. Okay, let me come back to the practical question. If we wanted to observe the bending of light ourselves, if we wanted to repeat Eddington's experiment, what would we need to do? Well, the easiest way is to wait for a solar eclipse and photograph stars near the sun during the eclipse. You measure their positions during the eclipse and compare them to their positions months later when the sun isn't in the way. The displacement tells you how much light bent. But there are other ways. If you're looking at light from a distant quasar, a very bright, very distant object, and there's a galaxy between us and that quasar, sometimes the light from the quasar gets bent around the galaxy. You might see multiple images of the same quasar. Each image is light that took a slightly different curved path around the galaxy. Or you can look for gravitational lensing effects in the light from distant galaxies. If there's dark matter between us and a distant galaxy, we can't see the dark matter, but we can see how it bends the light. The light appears distorted, stretched, magnified. The way it's distorted tells us where the dark matter is and how much of it there is. This has become one of our most powerful tools for studying the universe. We're using light bending to map invisible matter. We're using gravity as a lens. Now, I want to circle back to the mystery of why we're having this conversation at all. Why is this such a big deal? Why does it matter? It matters because it changed how we think about the universe. Before Einstein, space and time were separate things. Space was a stage. Time was what happened on that stage. They were independent. Objects moved through space. Time passed. They were disconnected. Einstein showed they're not disconnected. They're interwoven. They form space-time. And this space-time is not rigid. It's flexible. It can be curved. And the curvature of space-time tells us how objects move. This is profound. This says that the geometry of space and time determines physics. The paths that objects take, the way they accelerate, the way time flows, all of it is geometry. All of it comes from the curvature of space-time. And light, being massless, shows this most clearly. Light has no choice but to follow space-time. It has no inertia, no mass. It just follows the geometry of reality. So the path of light directly shows us the shape of space-time. When we see light bent around a star or around a galaxy, we're seeing a map of space-time. We're seeing geometry in action. We're seeing how mass warps reality. And here's the deepest part. Every piece of light that reaches us from the distant universe is a message written in space-time. It's a signal traveling through a curved geometry. The space it travels through has been warped by everything, all the stars, all the galaxies, all the dark matter between us and the distant source. So in a sense, all light is bent. All light that reaches us has been diverted from its original path. No light travels in a perfectly straight line across the universe. Every path is curved by gravity. In that sense, no light truly leaves a star unchanged. Every photon is shaped by the gravity it encounters. Every photon's path is a story of how gravity has shaped its journey. The light that reaches us is the light that curved the right way. The light that didn't curve the right way, the light that curved too much, that light never reaches us. It curves back or curves away or is absorbed or gets lensed somewhere else. So the question is, of all the light emitted by a distant star, which of it actually leaves the star and reaches us? The answer depends on gravity. The answer is geometry. And that's why light that never left the star might be a mystery, but it's really just the universe telling us what it's made of. It's mass curving space. It's space determining paths. It's light following the only way it can, the straightest path through curved space. Let me tell you what I think is amazing. A star sends out light in all directions. That light travels toward us. But before it reaches us, the gravity of other stars and galaxies bends it, changes its direction, displaces it, and yet enough of that light reaches us that we can see the star. We can see it displaced from where it actually is, but we still see it. And if we understand gravity well enough, if we understand how space curves, we can figure out where the star actually is. We can account for the bending. We can undo the curve and find the original direction. We can see through the gravity and find the truth. This is what Eddington was doing. He was looking at the curved paths of light and saying, I know how much space curves near the sun, so I can calculate how much light should bend, and if I measure how much it actually bent, I can test the theory that predicts the curvature. And he found that Einstein's prediction was exactly right. The light bent exactly as Einstein said it would. The space was curved exactly as Einstein said it would be. And so we learned something deep about reality. I'll leave you with this thought. Next time you look at a star at night, think about the journey that light took. Think about all the gravity it passed through, all the curves in space it navigated, all the ways it could have been bent but wasn't because it took the straightest possible path through curved space. That light reaching your eye is a triumph. It's a signal that survived. And embedded in its path is information about the universe, about gravity, about mass, about space itself. Einstein showed us how to read that message. He showed us that light doesn't travel straight through space. Light reveals space's true shape, and gravity is just space telling matter how to move. This is what nature does. It elegantly solves every problem with geometry, and light, being massless and pure energy, is the perfect messenger. It perfectly traces the curvature of space-time. It shows us what gravity really is. And that, I think, is the most beautiful thing about this mystery. It's not mysterious at all. It's just geometry.